Clinicians, a medical podcast that asks why. I'm Hannah Abrams, and I am joined for the 100th time by Avi Cooper and Tony Brew. Hey, guys.
Hello, Hannah. Hello,
100.
Seems like a round number.
We've done this 100 is a lot of times.
Yeah.
So I've convened.
So, over 4 years ago, on June 3rd, 2020, we released our first episode. And for this, for our 100th episode, we're going to reminisce a little bit on what we've learned. We're going to offer some favorites for episodes in which each of us was not the lead. And then at the end, we'll talk a little bit about some of our reflections on asking questions and staying curious. Sort of like when sitcoms used to have their 100th episodes. That's what I feel a little like we're doing today.
It's like the greatest hits.
Yeah, exactly. Some flashbacks. So let's start with some favorites. Tony, which one did you want to talk about? Which episodes?
Well, obviously I've got two. I got one for Hannah, one for Avi. And I'll start with a favorite of Hannah's. And that is episode 23. You probably don't remember based on the number, Hannah, but I will offer that it's an episode in which you seemingly introduced to the audience a new word that I certainly hadn't heard before bringing it to the episode.
I had first heard of it relatively soon before that episode, which was Benopnea.
That's right, Benopnea. Who would have thought we would dedicate an entire episode to what happens when you bend over? But it ended up being fascinating. Now, Hannah, you didn't invent the term, but I do feel like since we recorded and posted that episode, I've heard the term Benopnea significantly more than before we recorded that episode. And you kind of brought to the discussion two key points. The first was like, just what is Benopnea? Like, what's the definition? And for those of you who need a reminder, Benopnea is shortness of breath that's experienced during the first 30 seconds after bending forward. Benopnea. But I think the more important thing that you mentioned to us is that if you have Benopnea, it sort of signifies elevations in left ventricular filling pressures. So I don't know. This is one of my favorites because the idea that you could glean important information about LVEDP based simply on whether or not someone feels short of breath when they try to tie their shoes, I just thought that was so cool. And like I said, I've heard the term repeatedly since you talked about it.
You know, it's funny because, and I'm quite certain that when we did this episode when I was an intern, I did not share this part of the story. But the way I had first heard the term was that one of my co-interns who had, someone I was a little intimidated by, had kind of trained at all these fancy places, had used the term and like assumed that I knew it. And I was like, that's such an interesting word. And I've definitely never heard of it. And so I looked it up, and then I remember it came to me at like 3 a.m. When this guy was like, yeah, I'm only short of breath when I bend over to tie my shoes. And then I walk 7 miles and I'm totally fine. But it's just then. So that episode has a special place in my heart. And I'm glad I was not the only one who had not heard of Benopnea.
Same. I had not heard of it either. But I feel like I saw a patient not long after who also had it. I was like, Benopnea. But then I have incorporated that. And, we all carry around our like favorite teaching pearls and stuff. And Benopnea definitely made it into my quiver.
It's fun. No Benopnea for those patients.
No, definitely not. All right, Avi, so you're up next. So in episode 25, you asked, why can furosemide improve pulmonary edema from heart failure almost immediately? And I really feel like this episode had it all. The question is clinically relevant. It's got great physiology, and it really highlights something that many clinicians, including myself, frankly, just hadn't heard about, or at least hadn't heard like the mechanism of. And for me, it really helped explain something that I had observed but never understood. Like I had definitely given IV furosemide to patients, and I think I mentioned this on the episode. Like stared at the bladder, the Foley catheter bag, and like waited for the urine to come out, and assumed that if there's no urine, the patient's not going to feel better. But they started feeling better within 5 minutes.
The respiratory starts going down.
Yeah, and yet again, the Foley, like there's no urine in there yet. And one of the things you shared on that episode is some of the early data that showed that LVEDP. So again, we love LVEDP on this episode, on this show. You showed that LVEDP decreases as early as 5 minutes after the receipt of IV furosemide, and that's just crazy because it takes far longer than 5 minutes to start producing urine from furosemide. And you go over some of the mechanisms and how it relates to prostaglandin-induced venous dilation and increased capacitance. But really the key thing is that furosemide does a lot other than just make urine. And, for our patients, fortunately, it makes them feel better pretty darn quickly.
Yeah, speaking of, that's one that has always stayed with me.
It's pretty.
You give a lot of fluids, Hannah, so you're going to need some IV furosemide.
Yeah, it's dramatic. Honestly, one of my favorites about that episode too is also the sort of surprising things around like bronchodilation, like sort of stuff that was, you're just sort of realizing how, I don't know, how active furosemide is in our bodies, in our patients' bodies, that it's doing things that, we use it as a diuretic, and it's probably helping them in multiple ways when they're feeling better.
This idea of a drug being a dirty drug, like doing more things than you intend, sometimes
in a good way.
Maybe it's a good thing.
Yes, yeah, totally. I think in this case for furosemide, definitely. A
little bit of a panacea. Yeah. All right. Well, I have two favorites to share, and actually they similarly go back to our cardiology concepts that we talked about frequently, particularly in the early days of the podcast. And there's something that sticks with you so much about an observation, a physiologic observation that you can actually see on physical exam. And so I will always remember the first time that a clinical educator, Steph Sherman, pointed out Cheyne-Stokes respirations to me. And I could actually see this pattern that I had read about in a textbook that I had thought about. And in episode 34, Avi explained the mechanism behind Cheyne-Stokes breathing to us. And I'll say briefly that the idea is that people who have severe heart failure are at baseline hypocapnic, so low CO2, probably because the chronic congestion in the lungs leads to stimulation of those irritant lung receptors. And the thing that sets off this cycle of Cheyne-Stokes breathing is that patients drop below their apneic threshold to retain CO2, because they need to retain CO2 to return to normocapnia. But then the circulation time, because their heart rate is, or rather because they're circulating blood slowly with their heart failure, because they're circulating that newly normocapnic blood back to the CNS slowly, you're kind of always in a cycle of being delayed. So you're either overbreathing or underbreathing, and that creates this pattern of Cheyne-Stokes respiration that we kind of see clinically. So I loved that one.
And also, I think we talked about, I think it's probably, he was probably Cheyne, it was probably Cheney.
Oh, yes.
It's probably Cheyne-Stokes. Even though
we'll stick with Cheyne-Stokes. No.
We're not going to, it's not like Benopnea. We're going to change the conversation.
What I love about that discussion is, when you look at the breathing pattern, it's not like, if you tried to hypothesize, like, why would someone breathe like that? You'd probably struggle. But then as soon as you hear the explanation, you're like, that makes sense. And I love explanations like that you don't necessarily intuit, but once you've heard it, you're like, okay, I got it. I understand. And that, I think, fits well with Cheyne-Stokes breathing.
Yeah. And I love that every part of the mechanism relates back to heart failure.
Right.
And I think too, just, one of the ways that I like to teach this sort of part of our respiratory physiology is to think of the body as a thermostat. And that basically the brain and the lungs are talking to each other via carbon dioxide in the blood. And normally the thermostat, like, it's pretty quick, we can quickly respond. But in this case, the slow cardiac output, the sluggish cardiac output, it's delayed. So yeah, Cheyne-Stokes. Choked about.
Okay, now I have to remember the name. Yeah,
but I don't remember. Is that one person or two, Avi?
There's two people. There was two
okay.
people.
All right. So at least that I remember.
And So my second favorite one, and I'll say I love the fever episodes, which we have rebooted several times. So I wanted to focus on a different episode for this 100th episode, but
They're
special
like
shout
trees
out
get
to the,
fevers, trees get fevers.
yeah, trees get fevers, bees get fevers. It
Beehives
turns
get
out
fever. No, I think it's beehives. Wasn't it
beehives get fevers.
beehives?
Well,
The
yeah,
whole,
Anyways,
the
there
whole
was a
the whole
thing.
hive. Yeah.
Salamanders cross over into the warm environment when they have an infection. Anyway, if we sound ridiculous to you, please go listen to episodes 24 and 25 on the nature of fevers and why fevers are evolutionarily important. But the episode I wanted to talk about today is episode 18, which we have not talked about as much, in which Tony asked us the question, why is thirst quenched so quickly? So anybody listening to this podcast has experienced this. You're thirsty, you drink some water, and you immediately feel your thirst is quenched. But actually, that doesn't necessarily jive with what we might expect, because it takes about 10 minutes for your osmolality to return to normal, or to adjust after you drink some water. So, Tony, you walked us through all of the ways that, one, why we need thirst to maintain osmolarity, and effective arterial blood volume, and also the way that it's signaled by ADH and angiotensin 2, and specifically that there's two areas in the brain, the SFO and the OVLT, which receive these almost immediate inputs from the brain to respond to what we've eaten or drunk, to avoid a Cheyne-Stokes type situation where we overcorrect. And so instead, you only drink to the amount that you need, because the brain is immediately sensing it, even if osmolarity isn't changing immediately. So I love this one also, one, because it's something we experienced every day, but two, it's something where, oh, you might kind of give a hand waving explanation, osmolarity, but it doesn't quite line up with what you might expect.
When I was thinking about this episode recently, I was reflecting on the fact that one of the coolest parts about it is that those two structures, the SFO and the OVLT, which I won't try to remember their full names because they're exceedingly complex, but they're brain structures that live outside the blood-brain barrier. And that's the way that they're able to have access to like the blood osmolarity. And I don't know. I just the way that the brain is structured. Area postrema sits like somewhat outside the brain, outside the blood-brain barrier, so it's able to access toxins. This SFO and the OVLT sit outside the blood-brain barrier, so they have access to the sort of the osmolarity of the blood. It's just the brain is remarkable, and its ability to like put the structures in exactly the right spot. Unsurprisingly, evolution has afforded us that.
that really is a wonderful arrangement. That makes a lot of sense.
Yeah, put the structure where you want it.
And we have two of them just in case.
Yeah, exactly.
Well, my favorite, I'll start with Hannah's, was episode 89, Tusks and Tumor Suppressors, where you asked the question, why don't elephants get cancer? And they do get cancer, but much less often than you might expect, given that they're these huge animals with more cells than, say, like a mouse or us as humans. And Hannah quoted a study that suggested that elephants have a cancer mortality rate of about 5% compared to 20% or so for most other mammals, give or take, except for those poor Tasmanian devils that you mentioned that have a cancer mortality rate of an alarmingly high number of 50%. I think because that you said it was like an infectious cancer, basically, that they pass to each other. You also referenced the pedo's paradox. Was it pedo or pedo?
I think we debated this on the episode. And
Yeah,
I do
right.
Not know
how did we land? We'll just
I'm
say
going pedo.
Pedo's paradox, where most mammals, regardless of size, their lifespan, their cell number, they have about the same cancer mortality rate, which again that itself is sort of pretty surprising. That's a paradox in itself. But then a second paradox is that elephants are protected. That's even more surprising. And you talked about how, one reason for this protection is that elephants have a whopping 20 copies of the TP53 tumor suppressor gene, which essentially shields them against cancer when it arises. And specifically, it seems like elephants are able to efficiently undergo programmed cell death apoptosis, in a more efficient way when DNA damage arises. Which again, I loved this episode because it brought together. I think for my favorite episodes, my favorite things that we've done on the show, always bring together multiple levels and strands, and sort of we weave them together into a tapestry. And you really did that beautifully in this episode. Comparative biology, cancer genetics. You took us like sort of, way back in time, in sort of mammalian evolution. So really, really cool stuff.
Yeah, I like that we wove together some DNA in a double helix, but this was such a fun episode.
Yes, we did.
I'm waiting to have the appropriate opportunity to discuss this in clinic. It may never come, and I'm totally okay with that if it does, but for the right
you
patient,
have some control over that.
for the right patient who would be interested in this and for whom it would help them understand their disease. Yeah, I'm waiting.
Have you talked to has it come up with your preceptors?
I think, this is one of those facts actually that like, I think everyone knew before me. Like everyone else was like, yeah, of course, elephants. They have 1 million copies of TP53.
Well, what is the cancer syndrome? Is it Lynch syndrome that has the
Leaf-Romani.
Thank you, Leaf-Romani, where I don't know if you necessarily want to bring it up with the patient as Leaf-Romani to be like, hey, the sort of antithetical to you is the elephant.
Yeah. I think it's a great example though of the idea of evolution and redundancy, and
Right.
which does come up very frequently in clinic to kind of help people understand what's going on with them. But yes.
But the other interesting piece I thought too, which was a little bit humbling, was I think you mentioned that when sort of researchers have tried to add more P53,
that's right,
to mice, I think it was mice, to make it more protective. We'll have to go back to the episode, but in an experimental model, I think they were less fertile. There was like other things that
right.
sort of got thrown out of whack.
Yeah, it's thought elephants might be a little less fertile, actually, for the same reason, which is to say that evolution has found a way, and we can't just CRISPR more.
Yeah, we're just going to turn on more of that.
Yeah, exactly.
Won't stop us.
That was a fun one.
And so my favorite for Tony was Aquagenic wrinkling. This was episode 87. It was such a great episode. You asked the question, why do my fingers wrinkle in the bath? And I love this question because it's so elemental and universal. It started with an observation made by your daughter in this sort of like quotidian, way one evening when she was younger. And that her innate curiosity really inspired you on your own curiosity journey. And so, Tony, you talked about how aquagenic wrinkling involves the movement of water into the skin of our fingertips, which then leads to neurogenic vasoconstriction inside the dermal pulp, shrinking of the glomus bodies there, which then leads to retraction of the overlying skin. But because there are irregular attachments within the dermal pulp to the epidermis, you get this irregular contraction where some areas are pulled down and others are not. And that is wrinkling. You get wrinkles, but transient wrinkles. And then you also asked, why we have this feature. Like maybe again, thinking about evolution, is there some advantage or purpose as to why our skin behaves this way when wet? And you mentioned that there's a theory that perhaps it helps with gripping. And I guess there's some evidence that maybe some weakish evidence, some hand wavy
there's
evidence.
Some evidence
that maybe it helped us hunt in wet environments millions of years ago. You also mentioned the incredible clinical link with peripheral neuropathies, which can manifest with a loss of skin wrinkling because this is a neurogenic process. None of us have tested this clinically unless something's changed since this episode aired.
No, not since episode 87.
Because we would have to have the patient sit with their appendage submerged in water for like 20 minutes to have, to do the test. But it is available if anyone wants to try it. And again, I loved how this episode brought together lots of layers: physiology, evolutionary biology, clinical medicine. But most importantly, I think for this show, it was sparked by a child's fundamental curiosity about how the human body works. So I thought that was just that's like an emblematic, I think, I think that's an emblematic episode for our show.
Yeah, and my daughter Hayden and my son Cooper took a bath tonight, and and they were in there for a long time. And I can attest to the fact that, yes, Hayden's fingertips still do wrinkle. So the phenomenon, she doesn't apparently have a peripheral neuropathy just yet.
That to me is like the icon, or like the kind of cornerstone question that launched this podcast in a lot of ways. That is, why do my fingers wrinkle? Why is a cow?
I still don't know. Ask my dad.
So should we share some take-home points 100 episodes in on how to stay curious in medicine?
Yeah, I'll start. And so these are, as you mentioned, Hannah, not necessarily about the sort of medical stuff, more about like, what we've maybe learned about the process. And mine's very simple. And it's that, if you're curious to know the answer to a question, it's highly likely that others are similarly interested. And I've repeatedly asked a question internally and then said, I bet no one else really cares about this. And I have found that when I talk about it with the two of you or with peers, our profession is filled with curious people. Medicine is filled with curious people. And, humans more generally are curious. And so if you've got the question, there's an audience that's going to want to know the answer. So you got to start with the question.
And thank you to everyone who listens and is interested in our questions.
Yeah, no kidding, right?
We really do appreciate it.
What do you got, Hannah? Or Avi?
No, Hannah, go.
Well, I have two. The first is that I was struck as I was thinking about this, that the best questions really either came from patients or came from ourselves. And, our own observations about just our own lives and experiences, or the experience of talking to people who are having some symptom or some response to some medication. And sometimes the second best questions came from something interesting someone said in clinic that you then Google, or you didn't know that sort of everyone else seemed to know. And my second is that medicine is hard and curiosity is easy. The last 5 years in the world have been challenging. We have each kind of traversed a big journey. And this job is much easier when you can find bits of joy and bits of curiosity in it. So I am grateful, that we have this community and this podcast to do that.
Yeah, and I'll just sort of riff on that as well. I give a talk. One of my favorite talks to give is a talk on clinical curiosity. And one of my take-home points is that curiosity is a superpower. And it's especially in medicine, I think, because you can end up in a virtuous cycle where if you're curious and you indulge it in the way that Tony and Hannah just are talking about, then you learn more. There's probably going to be more, you're engaged with what you're doing and you're learning and growing. You're sharing that with those around you. I think the sort of joy factor rises. Team factors improve, team function stuff improves, all those things. And everybody's learning. And then the cycle just keeps repeating and you just keep sort of chasing those curious impulses. Everyone's learning gets accelerated. And so, yeah, I think curiosity is a superpower.
I've never been called a superhero, but I will take it.
This was festive and heartwarming.
It's the 100th episode. We gotta, zoom out a little bit, see the forest and the trees.
Yeah.
Cool. Well, hey, here's to 100 more. Awesome. Well, that wraps up our 100th episode of The Curious Clinicians. Thanks as always for joining us. Claire Morgan of notearly.com is our audio editor, and Giancarlo Bonomo is a producer for the show. You can join our mailing list at curiousclinicians.com to stay up to date on episode releases and have detailed notes delivered directly to your inbox. You can subscribe to our Substack at thecuriousclinicians.substack.com, and you can watch a video of this episode on our YouTube channel, The Curious Clinicians Podcast. Physicians and other healthcare professionals can earn CME and MOC credits from VCU Health just for listening to this episode. For more information, visit ce.vcuhealth.org/curiousclinicians. And as always, as we've done 100 times, the information contained in this episode is for educational and entertainment purposes only and does not constitute medical advice. Until next time, we've been the Curious Clinicians.